Okay, so today let's look at part 3 of these basic. So here's where we were. So in part 1 we looked at the CPU, and you guys remembered all the important details, that the CPU was divided up into ALU, CU, and then a piece of memory. Yesterday we analyzed memory in more detail. We talked about some words like volatile, non-volatile, RAM, ROM, persistent. We talked about cache. These are words that we pulled in. We talked about this idea that memory exists right on the CPU and then moves to RAM and then moves to eventually some sort of permanent persistent storage like the hard drive, depending on how much memory we have in different places. We also, in part 1, talked about the computer machine instruction code. Fetch, decode, execute, store, which was what this thing did. Okay? And then yesterday the words like primary memory, secondary memory, RAM, cache, and even video RAM and other aspects of RAM. Today, we want to go to the most simplest level, is with that hardware in place and that memory, what's actually being transferred around? When we use the word data, what do we mean by that? I mean, you guys know data. From the user standpoint, when a user thinks of data, they enter information like, for example, a name. Like, welcome to this program, enter your name. When you guys think as a programmer, okay, how is that interpreted? Well, name is really being stored as some sort of data structure. Okay, so that could be a simple variable, or maybe you're storing it in a class, or something more complex. But as a programmer, you're thinking that this piece of data is being stored as a data structure. But how is the computer taking your data structure and actually storing it? It's a machine. So ultimately, to the machine, it has to store it. Like, let's say it was saving this to a file. So the user enters a name, you store it as a data structure, and then you write it to a file. So it's going to be saved on some sort of magnetic device. We like to sometimes think of it as ones and zeros. But is it really ones and zeros? What is it? It's just electricity, right? This is really just electricity. Okay? Or magnetics. Okay, which is electricity, right? It's magnetizing and demagnetizing certain spots to make essentially what ones and zeros are. So today we'll look at this idea of data at that micro level. All right. Let's move on. Okay, here's what the curriculum says. Let me dim the lights. So the curriculum says the following about this particular topic. Here's what you need to know. Define the terms bit, byte, binary, decimal, hexadecimal. Not this one, that's just a different language, binary. 2, outline the way in which data is represented on a computer to include strings, integers, characters, colors. This should include considering the space taken by data, for instance, the relationship between hexadecimal and colors, et cetera, et cetera. So we're going to get into this today, okay? So the first thing is, let's talk about the real world versus the computer world. And this is the difference between analog and digital data, okay? In the real world that you guys live in, we live in an analog world, okay? When you see a movie, you know what you're actually viewing when you watch a movie is a series of pictures being flipped in front of your eyes so quickly. We know that, but we just accept it as a movie. We don't think about the individual pictures, right? We don't care where one picture stops and the next begins. We just accept it as a movie. We just accept that, okay? Our perception of the world is analog, okay? Analog data is a wavy line. When you're hearing my voice right now, you're hearing a variation in tone, up and down, going through pauses and stuff like that, and you're interpreting that data and turning it into meaningful words in your mind, okay? But in the computer world, it's not like that. It's either on or off. It's either 1 or 0, It's a digital world, okay? So the digital world is the computer's reality. Our world is an analog reality. So we need to think of the way that those two things are communicating with one another, okay? All right. So on or off, true or false, black or white, that's the computer's world, okay? 1 or 0, etc. But in our world, we still need to deal with the existence of living within analog data. I mean, how do we turn ones and zeros into the music that comes out of our iPods, right? How do we turn ones and zeros into a JPEG that we download off the internet? We need to translate between the two worlds. From a hardware standpoint, on pieces of hardware inside computers and other devices, they often have one of these two chips or both of them, an analog to digital converter or a digital to analog converter, an ADC or a DAC chip, okay? That's what happens, is you have hardware that can do this. So the second you have, for example, a phone that has a microphone in it, it is converting your voice, which is analog, into digital. At the same time, that phone is going to play sounds for you. So when it picks up digital data, it converts the digital data back to analog so that it plays a variety of sounds for you, okay? Now, you may have seen this in classes like physics or science classes. When they register analog data on different types of devices, it looks like a wavelength, right? It looks like that. I mean, if you're recording sounds, you often see that physical wavelength. But how do you turn a physical wavelength into digital data? Well, the digital data would not look like a wave. It would just be either off, like you can see here, or on. There is no in between. It's 1 or 0, but never in between. So a good example is a clock, right? If you look at that clock up there, that's an analog clock. At any given time you stare at it, it could be in between 2 seconds, depending on where that little hand is moving. But if you look at a digital clock, it's discrete. It's 1 second after another. There is no in between, okay? So that physical hardware to convert analog to digital, good example would be a microphone, like I talked about. Now let's go old school microphone, okay? Old school microphone, the way it works is it used a metal plate that when your sound waves hit it, vibrates, okay? So there's a very sensitive metal plate in there. So as you talk and your voice vibrates the air molecules, those air molecules will hit the metal plate, causing it to vibrate. The more it vibrates, obviously the louder the sound it's registering. So what's coming out of the other end of the microphone is an electrical signal, sometimes a very strong electrical signal, sometimes a very weak electrical signal, depending on what the microphone picks up. Same with something like photodiodes, which you could imagine in things like a scanner or a digital camera, where it's a material that absorbs light. And if it absorbs light, it converts that absorbed light into electrical energy. If it absorbs a lot of light, then we have a very bright image. If it absorbs very little bit of light, then it absorbs a dark image. And they have photodiodes for the different colors, right? So it's absorbing this much red, this much whatever. But that's still going to be turned into electricity. Lots of electricity or a little bit of electricity, okay? So then when it goes into the computer, it has to take those varied amounts of electricity and convert it into ones and zeros, okay? On the other end, when it takes all those ones and zeros and spits it back out, it goes through the digital to audio converter, usually through a series of resistors, to produce electricity of the right amount, okay? And that's analog. All right. This is done through a process known as sampling. So basically, what it does is it takes a wavelength and samples it at a few spots and says, oh, well, that's this number. Then it's this number. Then it's this number. The reason why we have different file sizes is because often of sampling. If you sample it more often, you're going to get a more accurate representation of the wave. Like, for example, if I was to draw a wave right here, but I only gave you 3 points. I said the wave goes here, here, and here, then you'd probably draw the wave like this. And you'd have a rough idea what the wave looks like. But if I said the wave was here, 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 and here, A little bit. Okay. You have a better, more accurate picture of the wave itself. It actually, if I was to draw it the most accurate, you're right, it would eventually go in like this, and down, like this, and like this, and then over there, and it's Elvis's face. No, sampling, okay? But what's the downs? Okay, so the advantage of sampling is you get a more accurate representation. What's the downside of more sampling? Yeah, larger file size, obviously, right? So more sampling means more accuracy, but more accuracy means larger file size. Okay. Again, some of this will be a review for you guys. Units of storage. So the word bit comes from the word binary digit. That's where bit comes from. It's the ones and zeros that the computer stores. That's what a bit is, okay? But you take a number like this and convert it to ones and zeros, and you get something like that. The question is, how is that actually occurring? How is numbers that we have in the real world turned into this? And I'm going to teach you that today, okay? But a couple terms behind it. 8 ones and zeros is called a byte, okay? Do you guys remember what 4 is called? Right, a nibble. So that's 1 bit. 8 of them is a byte, 4 of them is a nibble, okay? And a byte generally can store something very small, like 1 character, right? Then we have what's called the kilobyte. Okay, using the metric system, a kilobyte is 1,024 bytes. Now, do you know why it's 1,024 and not 1,000? You're on the right track when you say it's not base 8. It's base 2, yeah. It's because we're dealing with ones and zeros. It's actually not the same base. Like we use base 10. That's why a kilobyte or a kilometer is 1,000 meters. Is because we're using a 10 base system. The computer's using a base 2 system. So 1,000 to the computer is 1,024. It's just a different system. That's all. We'll get more into that in a minute. It's 2 to the 10th. That's what it is. 2 to the 10th is 1,024. So that's equivalent to like a page of text. 1 kilobyte. Then we go up to megabyte. Again, still not a round number because this is 2 to the 20th now. Okay? That's your megabytes. Megabyte's like a whole book worth of data. Then gigabyte, which is 2 to the 30th, right? So now we're just moving up in powers. The gigabyte is equivalent to a shelf of books, right? And then from there, obviously, would be the terabyte, which is 2 to the 40th, right? And we can go up from there. Bit, byte, kilobyte, megabyte, gigabyte, right? Here you can see bit is the smallest possible unit in our system, 1 or 0. Byte is 8 of those bits. Then from the byte system, we move up to 2 to the 10th, 2 to the 20th, 2 to the 30th, and then after that, 2 to the 40th. We also can go to smaller units, which we'll talk about in a minute. Actually, no, that's not in this part at all. Okay. So the bit can store a 1 or a 0, as I said before. You combine 8 of them to get a byte. This is also sometimes used, this type of terminology, when talking about computer speed. But in speed, they use the term hertz. Hertz stands for cycles per second. So if you think about that machine instruction cycle, fetch, execute, decode, how many of those can it do in 1 second is measured in hertz, okay? So a typical, for example, P3 processor back 20 years ago would operate around 500 to 700 megahertz. In other words, it could carry out about 500 million cycles per second. Now you think about what the common speed is of a modern computer. Anyone online right now? Christian, are you online? Yeah. Can you just go to like bestbuy.com while we're talking and pull up a new computer? Just some, it could be a laptop, could be a desktop, doesn't matter. And see if you can get a speed rating out of that. Yeah, the CPU speed. Okay. Now as well, in modern computers, they're also using like dual core, so they have multiple processors running at once and stuff like that, or even quad core processors and stuff like that. But what would be the general speed of a processor at this modern thing? Is it still, for example, measured in hertz? And if it's measured in hertz, what prefix are they going to use? Are they going to use mega anymore? Or have we moved beyond mega? Okay, I'll let Christian work on that while we're moving ahead. Okay. So here you can see from milli, centi, kilo, mega, giga, tera. It actually goes the other way. Now again, this isn't computer terminology. This is sort of Greek terminology. Milli, micro, nano, pico. So you guys probably know about some of these, like millimeter, centimeter, kilometer, right? And then you do hear these now in computer terms, right? Did you find a?
Yeah, 1.8 gigahertz.
Gigahertz, right? So if we go back, I was putting this slide together, I used megahertz. We're now moving beyond mega to giga. Before you guys check out of this life, maybe you'll be seeing terahertz, okay? Processors. Who knows? Who knows, right? Now, again, we can go the other way too, right? Like pico units are very small units, right? Nano units. So this wouldn't necessarily be used for storage, but this could be used for speed. You could say that it takes 1 picosecond for this thing to execute, right? Which means it's one whatever of a second that it takes for an operation to occur. Okay. So there are more common terms in the computer world. Kilo, mega, giga, terabytes, okay? The storage units are not in units of 1,000, but in units of 1,024 because it's measured in powers of 2, not in powers of 10, right? So you can also think of it this way. Kilobyte is 1,024 bytes. A megabyte is 1,024 kilobytes. And a gigabyte is 1,024 megabytes. And a terabyte is 1,024 gigabytes. It's big, right? Okay. But this is what I want to teach you guys. How to convert one to another. So we're going to start with the ability to turn binary into decimal and vice versa. Okay? So you guys are used to the base 10 system. But before we go any further, I'm going to show you what I'm going to recommend you guys do on an exam. When you get to an exam and you grab a piece of scrap paper, what I'm going to suggest is do the first few binary numbers just by hand in this way. We're going to have over here what the number is. Here's what it'll be in base 10, which is the world we live in, right? So when we count to 20, we count to 20. This will be the world of base 2, okay, which is the binary world of the computer. And we'll get started. Okay, so the number 0 in base 10 is still 0, right? And in base 2, it's also a 0. So far, so good. Then we'll go to the number 1. And in base 10, it's a 1, right? And in base 2, it's also a 1, because I can use those characters. Here's where the world changes, right? The number 2 is a 2, but I can't write a 2 there, okay? Just like in our base 10. So I'll leave that for now. And this would go 3, 3, 4, 5, 6, 7, 8, 9. Okay? But that's where in base 10 I would have to stop. When I want to draw 10 in base 10, I've only got those 10 digits to work with. I can't make another digit at this point. There isn't some weird digit I can use. I have to use a combination of 2 digits to draw a 10. Well, that's what occurs right here. At this point, I've run out of digits, so I now need to move to the next place order, the next column. So in order to draw 2, just like I did here, I basically just do that to make a 2. Because that's the next number I can use. Okay? So hang on, let's grid this out a little bit better. Okay? The 1 is the 1. The 2 is that. Okay? So now let's keep going. Watch me draw these marvelous grid lines. This is some low tech going on here. All right, here we go. Okay. So now we got to go to 3. Let's not overthink it. If you had to count to 3, but you were only allowed to use the numbers 1 and 0, what would be the next number you could count to as like a 5-year-old? You go 0, 1, can't use 2, 3, 4, 5, 6, 7, 8, 9, but you could use 10. What's the next number you could use? 11, right? Which is exactly right. That is the next base. What would be the next number you could count to? 100, that's right. And then 101, and then 110, and then 111. Okay, you're on the right track. What will be the next number after 111? 1,000, that's right. And then 1,001, and then 1,010. Okay, you know what's coming up next is 1,011. But at this point, let's stop for a second and see what's happening in base 2 world. Just using this placeholder, just this one. Yeah, do you see what's happening? It's alternating. Now, if we go to the next one, we have some empty spots here. What can an empty spot be filled with? A 0, yeah. So let's put a 0 there, and there, and there. Do you see a pattern in that row? Okay. By the way, this one's wrong. This is supposed to be a 1. That's why. That's why you're screwed up, because I put the red line over top of it. My apologies. Let's fix that. That was my fault. I can't draw. That's supposed to be a 1. Now, can you see the pattern? What's the pattern? 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros. So guess what? Yeah. So let's keep going a little bit. Let's go with 11, 12, 13, 14, and 15. Let's go up to 15, because I'm out of room there. Okay, and let me extend these lines down too. And while I'm here, I'm going to also draw the 3rd column line here. And then obviously I got a 4th column line here. Okay, so without even doing the counting thing, what's the next digit going to be here? And then? Okay, now tell me what's going to go here. And then? Ah, very good. Now, let's take a look at this column. We have some blank spots here. We can always fill in blanks with zeros. Okay. Do you see a pattern? 4 zeros, 4 ones. So this should be a, then 4 ones, right? Now let's move to the next one. These are all going to be zeros. There's 8 zeros. Guess what? 8 ones. That's the first 16 binary numbers right there. Base 2, base 10. You don't even have to know a formula to do the first 16. Now the 17th number, which would be 16 in our base, what will it be? Any idea? Yeah. And what will be the pattern here, do you think? Because think about it. This one went up by every other one. So it went 0, 1, 0, 1. This one went up every 1. This one went up every 2. This one went up every 4. This one went up every 8. What do you think that one will be? Yeah, 16. So there'll be 16 zeros. So then the next one will be a series of 16 ones. Then 16 zeros. Then what will be the one after that? 32, yeah. So you can see the way the bases work. So my advice is, when you get to the IB exam, just have this. Have this handy. It takes 2 minutes to draw. But I'm also going to suggest one other thing. Don't do this one. This is useless to you. It's the same as base 10. But there might be a base that you might also get a question on that's not base 2 and not base 10. Because base 2 is binary. Right? Base 10 is our real world. But there's also a possibility that you guys will get questions on base 16, which is called, anyone know? Hexadecimal. I know. Now, here's the way hexadecimal works. The base is how many characters you're allowed. So in our math, we're allowed 10 characters, 0 through 9. Those are our 10 characters. In base 2, you're allowed 2 characters, 0 and 1. In base 16, you're allowed 16 characters. So the way they work it is they give you the first 9 that we have in base 2. They go, okay, so you get you get those. But then they created new characters for the other 5. Do you know what they are? They're letters. They gave you A, B, C, D, E, and F. And chances are you've encountered these before. By putting together those letters and numbers, all 16 of those, you can actually create a number, right? So if I take an F, which really means 15, which really means this, combined with a 2, which means this, I've got something together, okay? You've probably seen these in things like web page codes, where they have these, or even color codes that use hexadecimal. But really, this quick chart is going to be super handy to you as you start in on these problems with base conversion. Okay, so let's move forward. Here's the actual way it works in math. B is the base, and it's represented by a series of digits. So in math, this is how we do it. So for example, 197.23 is really 1 times 10 plus 9 times, 1 times 10 to the power of 2 times 9 times 10 to the power of 1 plus 7 times 10 to the power of 0, okay? That's, or in other words, 1 times 100 plus 90 plus 7, because 10 to the power of 0 is 1. And then you can also go in the negative zone for the decimal. But you don't need to worry about decimals. That's in the old curriculum. That's the good news. And in our binary system, the base on this is base 2, okay? But when we convert to other bases, as I say here, memorize this chart. And you can see it was easy to do. The only part that's hard, like this is easy, just goes 0 to 15, goes 0 to 9, and then A to F. And then to do this one, which is really hard, you can do it one of a couple ways. You can just go 0, 1, 0, 1, 0, 1, then 0, 0, 1, 1, 0, 0, 1, 1, or just count normally. Because if you count normally, it's still going to work, just you can only use numbers that have 1s and 0s in them. So 0, 1, 10, 11, 100, 101, 110, 111, 1,000, 1,001, 1,010, 1,011, 1,100, 1,101, 1,110, 1,111. It just works, right? It's simple. But having that chart, believe me, will help you, as you're going to see in the future. Now, what if I give you a number that's not easy to do, like say not 16 or 5, but let's say I give you a number like 28. How are you going to do that one? Okay? So for this, I'm going to teach you a technique. It's not difficult. You do not need a calculator for this. To do 28, very simply, divide it by 2. Now normally if you were going to hand divide this by 2, you would draw it like this, right? I'm going to suggest a slightly different way to do it, which is instead draw that this way. Still the same division. So what's 28 divided by 2? 14, right. But again, let's say we were old school math people. We'd say 2 goes into 2 once, gives you 2. I subtract them, I get 0, I bring down the 8. 2 goes into 8 4 times, gives me 8. Subtract the 2 gives me 0, a remainder of 0. Remember that back in the day? What if it was 27? 2 into 2 once, gives me 2, gives me 0, bring down the 7. 2 goes into 7 3 times, gives me 6, remainder 1, and I was done back in the day. This is the key to doing this. 28 divided by 2 is 14. What's the remainder? 2 goes into 14 how many times? What's the remainder? 2 goes into 7 how many times? What's the remainder? 1, right? 2 goes into 7 3 times, that's 6, remainder 1. 2 goes into 3 times, how many times? Once, remainder? 2 goes into 1, how many times? This is the tricky part. 0 times, that's right. What's the remainder? 1. When you see a 0 right there, stop. Look what we got here. We got a series of 1s and 0s. Now the question is it the number this or this? You're right. Why? That's right, but that's not a good way to think of it, because that might not be the case. Because 111, if you go back to your chart, so if you go back to the chart, 111 is really 7. So that's not the right answer. But there's another reason. Could I keep going here if I didn't stop at 0? Can I go, what's 2? Really? Let's try that. What's 2 into 0? 0. What's the remainder? 0. What's 2 into 0? 0. What's the remainder? This would be infinite, wouldn't it? When you write a number, is there not an infinite number of zeros at the beginning of it? So in other words, this is the right answer. Because there would be an infinite number of zeros at the beginning of it when we do that conversion. There's not an infinite number of zeros behind it, because that's a different number. And that's how you do it. That's how you convert any number. Let's try one. Give me a 3-digit number. 364. Let's figure out what it is in binary. Divided by 2. Now you guys can do some mental math. I'm not doing it for you. What's 364 divided by 2? What? 182. What's the remainder? What's 182 divided by 2? Remainder? 91 divided by 2. Remainder? 45 divided by 2. 22 divided by 2. Remainder? 11 divided by 2. 5 divided by 2. 2 divided by 2. Remainder? 2 into 1. Remainder? And we saw 0, we stop. So the number is 1011011000. This is 364. Now, let me show you the world's easiest way to convert that into hex, into base 16. It would still work if instead of a 2 right here, you put a 16. You could do it that way. That's a little harder. Mentally dividing by 16 is probably not something you're going to want to do on your IB exam. So here's a trick. Take a binary number. So if it's not in binary, you got to convert it to binary, and group it from here into 4s. Now we also have this one. So how could I group this into a 4? Put 3 zeros there. Now, before you go, consult your chart. There's the chart that I said would be useful. So on the chart, I need this number, 1100. Where do you see that on the chart, 1100? Right there. Which is what in hex? C. So this is a C. Sorry. Now, this one, 0110, consult the chart. Where is that?
6.
It's 6, right? Oh, really? And that one's going to be 1. So 16C is that in hex. Okay, we're going to practice this next time, which would be, when are we meeting?
I'm not going to be here Thursday.
So last time, as we were just reviewing, we were converting from one base to another. And I showed you guys the basic math behind it. Just to skip ahead a little bit, that chart is super useful to you. You guys had no problems reproducing that chart. Just remember that the hex codes start at number 10 because it's now 1 digit and the digits are A through F. Okay? To do the more complicated conversions is the formula that we just did. And by the way, the reason I wrote it out like this is because you could write code to do this, right? You could write a while number, divide by, and you know that there's a code to obtain quotients and remainders. If you mod a number, you're going to get the remainder, right? Yeah. So here was the example I did with 375, and I did this with you guys last time. And now you guys seem to have a good one. Just watch that last one, right? That's the tricky one where the 2 into 1, because your number is going to end in a 1, right? So it's going to be a 1 on that side with an endless number of zeros in front of it, leading zeros. Now, when we go the other way, here's the formula. Start with a value of 0. For each digit working left to right, multiply the result by 2, and then add that 1 or 0 to that. Okay, so here's an example. I have the number 11010. Okay, so I start with a value of 0. I'm going to always multiply by 2 and then add that digit as I move going this direction. Okay? So I'm going to start this time, like you know how you guys started this way when you were, now we're going the opposite direction. So I'm going to start here at that first digit. Okay? So I start with a value of 0, multiply by 2, and add 1. Then that number moves to the front, and I do it again. Multiply by 2, add 1. That's the next digit. Take that number, move it to the front. Multiply by 2, add, in this case, 0. Take that number, move it to the front. And keep going until I run out of digits, and I'm done. Okay? So notice this number, 11010, is that number, 11010. Okay? So let's flip this back to what you guys did. Okay? So there's your number. So if I take this number, 1000111, and I apply the same formula. I start with a value of 0, I multiply it by 2, and I add 1. And this is going to go all the way down. 2, 2, 2, 2. Why 2? Yeah, but why did we divide by 2? What was the significance of it being 2? Because it's the base, right? This is base 2. Okay, so let's do some mental math. What's 0 times 2 plus 1?
1.
Moves here. What's 1 times 2 plus 0?
2.
What's 2 times 2 plus 0?
4.
What's 4 times 2 plus 0? Are you guys cheating yet? Are you cheating yet?
It's 8.
You're not cheating. You didn't see the cheat yet. What's the next number?
17.
Yeah, what's the next number?
30.
It's right here, you guys.
16.
35 times 2 plus 1. 71. So you see here, this formula is the reverse of this formula. Okay? So dividing by 2 or multiplying by 2, and we're getting there. So who's ready for the challenge? What's this? In base 10. So let's start by converting the hex into binary. So let's find the chart. So let's find 4 on the chart. What's 4 on the chart? So it's 100, right? What's A on the chart? Let's go. Yeah, no, but what's the binary digits? 10, 10, yeah. And what's 2? I shouldn't have to show you. Yeah, but it's 4 digits. So it's this. It's 4 digits. Okay, so now we have the binary. Now what do we do? So we put it down. 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0. Okay? Of course there is, but this is a tried and true method. Okay. What was the process again? These are going to be added, right? And this is important. The way you write it, by the way, will matter. If you write it the other way, it's not going to work for you. You're going to get a different. Right? Because wouldn't this also just be a bunch of zeros here, like forever? So 0 times 0, or 0 times 2 plus 0 is 0 times 2 plus, like it would be infinite number of zeros, right? This is going to be 2's. Yep. Okay. This would be timesing. This is fun. And then this is where we start with 0. Okay. Don't play games with me.
2. 4. 9.
What? 4 times, no, this isn't 5. What is it? 4 times 2.
Sorry, that was not on purpose.
Okay, I'm just going to write what you guys tell me. calculator's going to start to come out.
148. I gotta take the head back. It's constricting my blood. 296.
What is it?
296.
This is good for you guys.
We get a calculator. 592.
Five, what?
592. That was
That can't be right. Because you didn't add the 1.
1,186.
Yep. Got another method?
We know that these are all like multiples of digits. 1, 2, 4, 8, 16, right?
Yeah.
So like, just I do that number
Yeah.
there. Then we can just add the numbers that have all the ones.
That's right. Yeah. Jesse found another way I was going to show you, but Jesse's already, he's going to explain it to you guys now. So he's basically showing you that if you know the place value of the one's digits, that matters. So place value in base 2 is different than the place value in base 10. So as you can see, Jesse's put that's the 1, the 2, the 4, the 8. So what he's going to say is now let's add those. So the spot where there's a 1, which is right here, is 1,024. So he's going to write that. Go ahead. That was just my fault. Go ahead. Well, no, add the place values. So 1,024 plus the next place value would be 128 plus 32 plus 2. Go ahead. And then math, and then you get that, yeah. But let's see, right? That's 10 and 6 is 16, goes up. That's 4 and 1 is 5, and 3 is 8. That's right. That's a 1, that's a 1. You got it, right? So that's another way to do it, okay? Whichever way you guys want. Chances are you won't get super large numbers for your, any ones I've seen on IB exams were much smaller. They were small numbers. Okay. And as I said before, when you go to hex, by the way, you don't have to do the groupings of 4. If you look at what we've done up here, all you do with hex, you could put 4a2, is that 2 becomes a 16, right? But that's, you guys had trouble with multiplying by 2. Now do mental math with 16. That might be a bit tricky, right? But you could do the same thing. You could go 0 times 16 plus 4. So that'd be 4. 4 times 16. Anyone want to do that one? What's 4 times 16? Plus a, which is 10, which is 74. So it'd be 74 times 16 plus 2. And as Jesse said, using math, you're going to get 1182, right? So it's the same basic process. All right. Insert math here. Okay. So as I was just saying, I think it's easier if you just do the grouping and use the chart. That'll be much easier for you. But you may want to practice a few of these, okay? So here's an example. Again, given this value, you could group the 4s. Yeah, special effects. And then don't forget, you can always have a bunch of zeros at the front, okay? And then I can now pull out the 2a5. And if I want to go the other way, and if I was given, for example, these 3 hexadecimal values, I can turn those into binary values, and then in theory I could then turn those binary values into base 10 values. So, and you can do this, by the way, with any base. You can choose, like there's actually, in some computers they use octal values, which is base 8. It's rare, but they do occur in some places. So what does this mean, right? So I've got all these values, all these numbers. How do they represent things other than numbers, right? Because that's important. So for example, everything in the computer is just a pattern of numbers. And those numbers ultimately just become 1s and 0s, which is binary, which ultimately just become positives and negatives. So if we're going to do something like decimal numbers, that would be slightly different, right? Because which do I store, the front part of the decimal or the back part, and how does it work? And what about things that aren't numbers? Like, say, Boolean values. Well, that was probably easy, 1 and 0. But what about letters? Okay? What about colors? What about images on the computer? Right? What about sounds on the computer? So early PCs used an 8-bit or a 1-byte register length. So they said, we're going to store stuff in 8 bits. Okay? Now, as computers have advanced, the number of bits they assign to each sort of thing on the computer has expanded. But if you only use 8 of them, there's only 256 possible combinations of stuff. This now relates to something you guys have seen since the first time you were in here. This thing back here, in the back of the room, the ASCII table. It is a way you can look up letter patterns, okay? The pattern matters, so we need sort of a lookup table. There's a unique number of combinations, though. So if we're only using 8 bits, we only have 256 possible combinations we can use. If we expand that to 32 bits or 64 bits, then we have way more number of combinations that we can handle here, okay? What's important is that we all agree that a certain number of bits equates to, say, the letter C or the letter Q. Okay? Or the character exclamation point. So this is the protocols or the rules that the computer systems follow for representing these values. The most common is the ASCII code. The ASCII, or the American Standard Code for Information Interchange, says, oh, you want to store capital B? Then it'll be code 66. And there's, on that chart, it actually shows you the binary value for 66 as well, or the hexadecimal value for 66. And if you want to store, for example, the character exclamation point, it's going to be value 33 on the table. And this also includes values that aren't printable characters, right? Like a space, or some of these early ones were actual sound values and signal values. So it would, like this one here, ACK is an acknowledgement signal. So when you were transmitting data and you got this code 6 back, it acknowledged that you received the data, right? And then this one was, like one of these is like an old-fashioned beep sound and stuff like that. Some of these are a little bit, there's the null value, by the way, at the very top. Some of those are sort of out-of-date characters now, but they still exist within the table, the ASCII table. Okay, so ASCII uses an 8-bit register. So that's why, by the way, you have, this isn't even 256. This is only 128 characters so far in the ASCII table. So I was able to cover the entire alphabet and most of the punctuation characters that I need, okay? So it's expanded, obviously. There's still more that can be put into that, okay? Because they use 7 bits. They don't use actually all 8. One of the bits, often called the most significant bit, shortened often to MSB, is what's called a parity bit. This is a bit that's used for checking whether or not you actually received the right data. In the previous curriculum, I had to sort of explain to students in detail what a parity bit was. I'm going to reserve that. We're going to maybe do that if we have time, because it's not really necessarily part of the new curriculum. But it's basically just a check bit to make sure that when you're transmitting data, that the data got transmitted properly. So it's like a little safety net that gets added on there, okay? So every time you press a key on a keyboard, it is sending a signal to somewhere in the computer to look up on the ASCII table what character you want to use, right? Oh, you want a K. Okay, so you've got to send along this particular code for K. So it's very simple. It's just a lookup table for that. Okay? So the character A, capital A, is looked up as a 65, and it changes it into 1s and 0s, which eventually gets pumped through your computer as positives and negatives. Okay, and the letters as well. ASCII as well also includes those non-printable characters, like beeps and acknowledgement protocols for transmission of data and stuff like that, like ringing the bell and acknowledgement and stuff like that. Okay. So that's characters, right? And we talked about Booleans. Now what about graphics, right? Like how does a graphic become a graphic from 1s and 0s, right? If you download a picture of, you know, a squirrel water skiing or whatever off the internet, how did that happen, right? So let's jump here for a second. Let's make a super simple picture, okay? Ready? Here it is. Super simple picture, right? So if that was going to be transmitted over the internet, what happens is that picture has to be mapped out on the screen, right? And as a map on the screen, it has to draw all the little pieces of that picture, or pixels. And does anyone remember what pixel stands for? Picture element, right. Picture element. The X is just because it's cool. That happens a lot, right? X's happen. Mac likes to say OS 10 and they use an X. There was Windows XP, right? They like the X. They like the X, they like the I. Those are favorite values in computer science. So, okay, so I'm going to map out that drawing up there. So the first thing maybe I'm going to do is to the outside of the circle of my happy face, right? So I'm going to map out that, okay, just coloring in some pictures, some pixels, right? There we go. There's the circle. Now we'll map out the eyes. Looking good. And now I'll map out the smile. We're good. So this can be turned into that when it's transmitted over the internet. Now, how will I take this and turn it into ones and zeros? Well, you guys know from your studies in arrays and in programming that this is really a 2D array, but does it have to be a 2D array? Could I just take each row and line them up one at a time, right? Like, could I just take this row and then follow it by that row? In other words, if I took this row out and just put it after here, as long as I know where one row ends and the next row begins, it would just be a long series of ones and zeros. Just like running a for loop, it would go through one row, then the next row, right? Now, if I was only using two colors up here to draw this, black and white, then I would only need two values for each pixel. So I'd say, okay, this is a 0, and this is a 1, right? So what would happen would be the pattern would come out, 0, 0, 0, 1, 1, 1, 1, etc., right? But I would need a little bit more information than just that to draw the picture, right? I would need a little bit more information in terms of it's how many rows times how many columns. That needs to be known before I can draw it, right? I also need to know this before I draw it. I need to know the dimensions of this thing. And this is what's called the color depth. Oops. Because if I want to use 16 colors, this wouldn't be a 0 anymore. This would be one of 16 different values right there, which all of a sudden makes it quite a lot more. And now I have to convert that number between 1 and 16 into a binary number. So I need to know this. This information, when you send a picture, the color depth and the dimensions, is usually put in what's called the header section of the image file. So you're about to send an image across the internet. The first part of that file is the header information, which gives you information about the color depth and the dimensions of the picture to draw the map. Once it has that, then it can just start feeding it all the ones and zeros to actually map out the image. That's what a picture is. It ultimately is still ones and zeros, but done in that way, okay? Now, there's one other way it can do a graphic, okay, before I show you. Because it could also go another way. That's what's called a map graphic, okay? Sometimes called a bitmap graphic, depending on sort of the system you're using. But what if I just gave you part of the header information? What if I said, I need you to draw a 4 by 5 two-color image. Okay, 4 by 5 two-color image. Would you kind of go, okay, 4 units by 5 units, and then I also told you it was a rectangle. Would you have enough to draw it at this point? If this is 4 and this is 5? You know what a rectangle looks like, right? So if you know what a rectangle is, whoops, you get the idea. You could draw it. Now what if I told you it was a 4 by 5 triangle? Would you know how to draw it? How would you draw it? You'd probably draw it like this, right? What if I told you it was a 4 by 5 circle? or maybe circle's not the right word, sphere, or ellipse, yeah. Well, what would you do? Jesse, what would you do? Okay, no, don't over-explain the math on it. You would draw essentially a rectangle and then fill the rectangle with that, right? You may have heard the expression that this is what's often called the bounding box. You guys might even call it the hit box if you're making a game. It's the box around the image you're drawing within it. But how many of these can I give you? How many shapes can I give you? Is it infinite? Yeah, it's not really infinite, is it? If I was to say, now let's pick a letter of the alphabet, like the letter D. Trying to draw it all nice. Can you turn that into simple shapes? Yeah, a circle and a line. Okay, what about the letter X? You could maybe make a bounding box around it, and you could draw that one. Things get a little more complicated though, right? If I say capital T in Times New Roman, and it has these little guys on it too, like all curvies like this. Capital T in Times New Roman. It's still possible, right? You could actually get in there and actually do all the mapping to make that into just equations. But what if I said it's a picture of your face? Anyone want to do all the math on calculating all the angles and values to do your face? So there are some images that it's too difficult to do that with, and then there are some images that you can actually do this with. You can actually map them out in terms of the math behind it. And that's what we're talking about here. We're talking about the difference between a bitmap graphic, which is just a pure map, and what's called a vector graphic. A vector is a physics term that essentially means I can do the math to calculate it. A bitmap, like we just said, is just a map of all the individual pixels. Tiny squares drawn out using the colors that... Now, bitmaps are also sometimes called raster or raw graphics. It depends on sort of the flavor of the month, which way you're going with it, okay? 1 pixel per map point, okay? And then more bits per pixel depending on the colors, right? Or the pixel depth of that particular pixel. So black and white images, 1 bit per pixel, 1, 1, or 0, okay? The greater the range of colors you're going to add to your image, the higher the pixel depth, right? So if you use 24 bits per pixel, you can have up to 16 million colors in your graphic. That's pretty good, right? So to think that if you had a 10 by 10 image that was using 24 bits per pixel, you'd have a small image, but you could have up to 16 million colors, which, by the way, is kind of silly because the human eye can't even see that many colors. But that's how many you can actually... You can produce more colors on your computer than your eye can actually pick up. The more colors, the greater the pixel depth, but the greater the pixel depth, the bigger the file size. So there's always that trade-off, right? Vector graphics don't work that way. They work based on calculations, object calculations. So it's all math with vector graphics. So here, for example, is how they would calculate, say, the capital letter A. They'd actually measure out distances for curves. They would draw triangles. You guys may remember back in grade 11 when I did the infamous example of the star, when I did the graphics unit, and how you guys complained how it wasn't a good enough looking star. But remember how just to do all the math just to draw that star, and we didn't have curves in that, it was a lot of work just to get the star on the screen. So now you can imagine this happening. And this does, by the way, happen a lot. Every single font you use on a computer does this for every single letter of every single font. Okay? But because it's storing a calculation. When you store the calculation, it actually reduces the file size, because now you're not necessarily storing the entire map. Now, why would fonts want to store a calculation rather than the map? Exactly right. When you change the size of a font, you just plug new numbers into the calculation. Rather than store maps for every single size, you just store one calculation and then plug new numbers into the calculation, and you get a new size of font. So in the case of the font, that works out really well. Can you think of another thing that works on the computer that way, where you resize it and it resizes really quickly? Well, Windows, maybe themselves, but what about clip art in programs like Microsoft Word? Or if you're using a program like Photoshop and you draw a square using Photoshop. Notice how when you resize it, it is really fast, and the edges of it are really clean looking. That's because it's actually storing that graphic not as a map, but as a calculation at the time, okay? You don't need to worry about this usually because this is what's happening behind the scenes. But this is what's happening to a layman, right? They see two different circles, they think they're the same circle, and this is classic grade 9 behavior until they blow it up or they zoom in. And once they zoom in, they'll notice the difference between the two graphics instantly. That this sort of, and you'll even hear the words, it's all pixelated, right? You hear that term. But what that really means is this top graphic was a calculation. So that when you resized it, it recalculated and got a much smoother line. Whereas this one was just a map. So when you resized it, you're just seeing closer pieces of the map. It's like taking a map and pulling it closer to your face. You're starting to see the individual parts of the map, whereas in the calculation, it's just recalculating it for you, okay? So the bitmap graphic has the advantage of storing it exactly, but the vector graphic has the advantage of resize and stuff like that. Why doesn't everything become a vector graphic? Because some things are just too hard to calculate out, right? They are cleaner. They have the advantage of that, but they are just sometimes too complex. Like a photograph, you can't do all that math. By the time you did it, it would be a ginormous file size anyways. There'd be just so many elements in play that it just can't work that way, okay? But this is some things that need to be thought about as a programmer is, how am I going to store this data in the most efficient way? And sometimes it's a balancing act between how realistic I want it to look versus how well it's going to process when it's working in terms of that. But then you can add the other element to it is, well, okay, I'm storing it as a map. Can I reduce that file size even though it's being stored as a map? And for that, you use compression software, which essentially just means algorithms to look at the patterns of ones and zeros and try and reduce the number of ones and zeros. So chances are you'll probably do a program like this in university. I know I did several times. And that is, if I go back to here and I think about all the ones and zeros that would come out from this map, I would eventually find a pattern to this. Possibly that I could save space by saying, well, that's just a bunch of zeros. And this is going to be a bunch of zeros right there. And even here, look at this. This would be a whole ton of zeros. So I could marker that by saying 0 times 1, 2, 3, 4, 5, 6, 7, 8. 0 times 8 spots would be a lot faster, maybe, than actually drawing out all those 8 zeros. Depends, right? Depends on that. So I'd have to write an algorithm to do that. And that's essentially what compression algorithm does. The thing that you'll probably do in university that I did is you have to make this thing called what's called a sparse matrix. Okay, so you guys know what a matrix is, right? It's a 2D array. What you'd have is this thing that's a 2D array, but it would be mostly zeros. That's where the word sparse comes in. So they'd give you a 2D array of mostly zeros, and then they might throw a 1 in it in a few places. And they'd say, what's another way you could store this other than as a 2D array? And there are several different ways you could do that, but some of them involve things like linked lists, where you link together a whole bunch of zeros or a spot, and then you just link to the actual spots where the ones are, right? So you'd remember the dimensions, and then maybe just remember the coordinates of the ones depends on the patterns there. And so these things called sparse matrices are often a big part of programming at the next level to think about ways you can optimize storage space in compression software. At the simplest level, compression software is an algorithm that reduces the file size. Compression software include file formats like JPEG. That's what JPEG stands for. Well, it's not what it stands for, actually. JPEG is actually properly pronounced JPEG, not just JPG. It became JPG because some file systems only allow 3-letter extensions. Modern operating systems allow 4-letter and multiple-letter extensions. But JPEG stands for Joint Photograph Experts Group. It's a group of programmers who claim they're experts working in photographs in a joint conglomeration to come up with the standards for storing this. Now, this is the one that was controversial. That one stands for Graphics Interchange Format, which is why it should be pronounced GIF and not GIF, okay? I know that someone on the internet has posted that the originator of that graphic, which I dispute in itself that it was one guy who actually came up with that, but that's a different story, says it's pronounced GIF. And believe it or not, this was actually a thing on, I think it was the Big Bang Theory. One of my buddies sent me a thing that apparently on the recent episode of the Big Bang Theory, they debated the pronunciation of GIF and GIF. Okay, but ultimately it's just this. You put your software in or your file in, what comes out is a compressed version of that file. So I want to make it simple for you with some sound effects. You want them again? Yeah, okay. Florian.
What kind of compression is
TIFF, I don't remember. I don't know if it is compressed. I think that might be a raw format. So as I said to you guys before, there's the idea with the header and the signature part of the file when it comes in. Things like height and width or rows and columns, and then how many colors to use. So here's a graphic that represents that. So you'd go, okay, it's going to be a bitmap graphic. It's going to have this width and height, and it's going to have 2 palette colors, 2 pixel depth. At that point, the header section of the file would end, and then all the actual data would start streaming in. And from that, it would be able to draw the graphic, right? It would be like, okay, I know it's a bitmap graphic. Here are the dimensions. Here's the color depth. Give me all the data. Okay, I'll draw it for you. That's what it is, okay? That's the pattern. Here's some data about that. If you go to 8 bits per pixel, you get 256 colors, okay? If you go up from there, you get more and more. Then again, they do other things. Like they have these things like virtual pixels where they know that the human eye tends to blend colors together. So when they draw these things, they often do it in a way that, you've probably seen that if you've ever zoomed in on a graphic, that some of the pixels are kind of blurry. But when you zoom back, it looks clean. That's because of our human eye and some of the perception things that the human eye does. Don't worry about that. If you go up to 24-bit, you're up to, again, 16 million colors. Okay? So the pixel depth determines the colors, determines the file size. Whew. All right. Then at the hardware side, when it gets down to positives and negatives or electrical impulses, then it gets fed into things like your actual graphics adapters and your graphics cards on your computer, and it adjusts the electronic signals that are producing the actual glowing image you see in front of you when you look at it. And that goes through that digital to analog conversion process. Because by the time you look, like right now at this projector screen, or you look at the screen in front of you on your computer, you're not looking at ones and zeros anymore. You are looking at light being projected at your eye, and in order to produce that light, it needed to have a wavelength of electricity at some point. So at one point, it had to turn the ones and zeros into a wavelength of analog signals. And do you remember the name for the process to determine how accurate that becomes? Remember we did the example with a wave, and I said you could just have 3 points to create the wave, or you could have like 30 points? Sampling, right. Sampling the data, okay? I then go on to explain how this would actually work on a monitor. I think maybe we'll skip that today, but the way it works on a monitor is basically very intense electricity heating up phosphorus material, and they have 3 phosphorus materials for the 3 basic color values, and it would heat up from there. Just so you guys know, that's the end of part 3. But there is more to this, that if you want to read more about this, there's bonus content that follows. I'm just going to skip through it quickly. This is from the old curriculum. It's nothing you guys know. But it does explain how to do the decimal portion of a number, which used to be part of the old curriculum. So you need to have to convert floating point numbers as well. It shows you that you would do the 43 part the way you guys know how to do. Then to do the 6.25 parts, the way you do that is a slightly different formula, right? Using truncation and stuff to generate the binary number that way. Okay, again, I'm not going to go through the detail, just know it's there. And then to convert back, I also have the formula there, which is a similar format. So here, I would convert back to 26 from that portion. And this one, the formula switches around slightly to get the decimal portion. Okay? Again, not needed by you guys anymore. And then I also talk about how you could do this with any base. I just showed an example of actually dividing by 16 on here. Again, I'm not going to do this and how to go back. Why hex? We've already done that. I actually do some adding and subtracting of these binary numbers. And again, We'll actually cover a little bit of this in part 4, so I'm going to skip through that real quick. But no, this is all in there, some stuff like that about binary addition and subtraction. We are going to do a little bit of that next time. And then hex addition and subtraction. That's nasty. You don't want to do that, okay? It's really nasty, using letters and numbers. And then something called 2's complement, which maybe we'll touch on briefly next time. I'm going to just stop for 1 sec and jump right back to here. This is the important part. Refocus on what you need to know, right? This is where we started last time we met. So now let's see how you guys would do. Define the terms bit, byte, binary, decimal, hexadecimal. I'm not going to ask you to say it, but you should feel fairly confident in at least knowing what those words mean. It outlined the way data is represented by a computer. And it says, from strings to integers to colors, considering the space and the hexadecimal representations. Do you feel like you have an understanding of how the computer stores data? That would be my question. And I hope I've answered that. I hope that you guys feel fairly confident about that.